My name is Samira. I performed my PhD on nanoscale fluorescence-based cool materials under supervision of Professor Matt. And I'm currently working as an ESD consultant at Arup. First, bit of information about different generations of cool materials. The very first generation were light-colored cool materials presenting a very high reflection, but there were some issues associated with the light-colored cool materials, including the serious issue of glare, and also because of the aesthetic considerations. We cannot apply the light-colored cool materials at a very large scale. So the second generation proposed by researchers were the so-called near-infrared reflective cool materials. So you may, using this so-called near-infrared reflective materials, you can have the same color while having a lower surface temperature. And the reason is that we have exactly the same reflection in the visible range. So we can have exactly same color, but these materials present a very high reflection in the near infrared range. And that's the reason you can have materials of the exactly same color, but the cool, let's say, materials of the same color present much lower surface temperature. And the next generation are so-called fluorescent materials. So one of the limitations of near-infrared reflective materials is that they cannot, they are absorptive in the visible range. So with the introduction of fluorescent materials, we are aiming to target the incoming radiation in the visible range. How fluorescent materials work is through re-emission of the absorbed light. In this case, you can preserve the color, but the incoming radiation is re-emitted through so-called fluorescent cooling. The very first tests on fluorescent materials have been performed on bulk fluorescent materials. But in my PhD, I investigated the possibility of application of nanoscale fluorescent materials. With, let's say, so-called bulk fluorescent materials, one of the limitations is that the fluorescent materials are the intrinsic properties of materials. So you cannot adjust or modify the fluorescent properties and the fluorescent cooling potential. You cannot enhance the fluorescent cooling potential because it is an intrinsic property of that material. But with the use of so-called nanoscale fluorescent materials, also known as quantum dots, there is a possibility of adjusting their properties and enhancing their cooling potential. Also, the other interesting point about these materials, because these materials are semiconductors and they present a very high they let let's say a light to go through them. So with this, we are able to integrate them with so-called near-infrared reflective materials and achieve a very high cooling potential. So the fluorescence cooling effect, I just mentioned with conventional materials. The very first research was performed with Ruby, and which has they achieved up to 5 or 6 degrees lower than the equivalent non-fluorescent materials. And with the quantum dots, which I will present later, there are possibility of adjusting their fluorescent properties, which I will explain more in detail. With fluorescent effect refers to the radiative or non-thermal relaxation of excited photons. So the first, when the light is absorbed by the material, there are different processes. We have some thermal losses, including thermalization, which is the number 2. So the electron is excited and goes to the upper energy levels, and then it returns to the conductive band. So this process is a thermal loss, and then some of the photons will release their energy as light, which is known as fluorescence. So this is what we really want, is that this material can release its energy through a non-thermal process. But some of the photons will still release their energy through thermal processes. This can be due to some mechanisms and some surface defects in the material. But as I said, with nanoscale fluorescent materials, we are able even to overcome these surface defects to and enhance their non-thermal radiation. So the properties that we can change with quantum dots, one of them is the absorption edge wavelength. The absorption edge wavelength is the wavelength at which the nanoscale fluorescent materials re-emit. So with changing the size of our particles, we can change the wavelength at which they re-emit energy. And you know that at each wavelength we have different levels of energy. And also this can allow us to have fluorescent materials of a different color. The other important thing is the quantum yield. As I mentioned, with not all of the photons can release their energy through lighting. So some of them will emit through thermal radiation. What we can do, and some of them also, just imagine when we have the light inside of our material, some of them may also re-emit and reabsorb the light. So the distance between these nanoparticles is also a very important factor. So by adjusting the distance between these particles, we can avoid this process of re-emission and reabsorption. And also another thing that may happen is the surface defects on the surface of quantum dots. And one of the common solutions to overcome this and to enhance the quantum yield, or somehow to overcome the thermal radiations, is to have a shell of another semiconductor materials. Also, the thickness of this shell plays an important role. So like all of these things can be modified in order to enhance the quantum yield and the corresponding fluorescent cooling potential. So the other things that we have is the thermalization loss. So apart from the non-thermal radiation that I explained about the distance between the process of reabsorption and re-emission between the particles, also the surface defects. There are some other thermal mechanisms, including the thermalization loss and the transmission loss. So this is basically because of the mismatch between the energy of incoming radiation and let's say the wavelength of re-emission. Because with re-emission, we will always it will be only from the conduction band to the valence band. But when we have a photon with a high energy, so we will have some part will be released as thermalization loss, and if the energy is lower than the band gap energy, then we will have some transmission loss. So taking this into account, the thermalization loss and transmission loss, we have calculated what is the theoretical limit of fluorescent cooling for quantum dots of different colors. In this case, we assume that we have a quantum yield of 1. So there is no thermal loss through quenching, but we assume that we will have this thermalization and transmission loss. And based on that, we calculated that for a blue emitting, green emitting, yellow emitting, orange emitting, and red emitting fluorescent materials, we can have 15% up to 43%. We can reject between 15% and 43% of the incoming radiation. This is also, so within that, let's say, just assuming that we will have that transmission and thermalization loss, we calculated what is the temperature reduction potential for at different times of the day, and with quantum dots re-emitting at different wavelengths. As you can see on the figure on the right, quantum dots with a re-emission wavelength of 300 nanometer present the higher temperature reduction, which can be very high, up to 35 degrees, compared to a conventional non-fluorescent material. But like here, we assume that we have 100% quantum yield, but we still have the thermalization and transmission loss. And then for quantum dots with 500 nanometer present the lowest temperature reduction potential. And the figure on the left shows how what is the temperature reduction if we have quantum dots with different quantum yield percentage between 10% to 100%. You can see how the temperature reduction would be. Let's just say if we have 15%, we can still have a temperature reduction of 15 degrees. We also calculated how quantum dots can help us to increase the reflection with so-called ESR, or effective solar reflection. Effective solar reflection is solar reflection plus the re-emission via fluorescent materials. So as you can see, we can have like in this figure on the bottom left, you can see that even for materials having a very high reflection, let's assume that the absorption is 100% and reflection is 0%, we can still have something around 0.2 or 0.3 of effective solar reflection, which is a very good number. And as we move to materials with a higher solar reflection, you see that the difference between effective solar reflection and solar reflection decreases. So, and also on the photos, on the figures on the right, you can see how the re-emission wavelength affects the effective solar reflection. As I explained also earlier, the maximum potential is for quantum dots with an absorption edge wavelength around 1200 to 1300. And also here we calculated how solar reflection and quantum yield can affect the re-emitted energy. So with let's say absorptive, highly absorptive materials, fluorescent materials, we can have much higher re-emitted energy. But even with quantum dots with, let's say, 0.5 solar absorptions, we still have a very high re-emission energy of something around 200 watts per square meter. So the previous slides showed you how we can optimize our material, our fluorescent material within the theoretical limits that I just mentioned. Now, is it possible to even go beyond that theoretical limit and have a very optimal fluorescent material? Yes. So we can really control the transmission and thermalization loss. One of the techniques for to overcome the transmission loss is through up conversion of 2 photons. So we can up convert 2 photons with energies lower than band gap energy into 1 photon with an energy level higher than the band gap energy. Another method is through transmission loss, which again, as I mentioned, transmission loss can be minimized through application of a near-infrared reflective materials. That means having our fluorescent material as a top coat, and then having a near-infrared reflective materials underneath. So the fluorescent material can somehow re-emit the incoming solar radiation at shorter wavelengths, while the near-infrared reflective material, the subcoat can reflect the incoming solar radiation in the near-infrared range. Also, with thermalization loss, we can have exactly the opposite process, which is called as down conversion. So we can down convert a photon with a high energy into 2 lower energy photons. And I also explained about the quenching loss, so I'm not going to repeat that, which is through the reabsorption of to reduce the reabsorption and also controlling the surface defects. So we calculated how the thermalization and transmission, we somehow quantified what are the thermalization loss and transmission loss for quantum dots with different absorption edge wavelengths. So this can allow us to propose the most effective methods to overcome the non-radiative losses. Let's just imagine if we have a fluorescent material with an absorption wavelength of 600 nanometer, then the transmission loss is much higher than thermalization. So in this case, maybe integration with a near-infrared reflective material or up conversion could be the best solution. While for a quantum dot with, let's say, 1500 nanometer absorption edge wavelength, then the down conversion is the best solution. We have also calculated the different components of thermalization loss, of thermal losses, including thermalization, quenching, and Stokes shift for different wavelengths. Again, to overcome the losses for each of these mechanisms, there are methods. So we were trying to see how these thermal losses are changing based on the absorption edge wavelength, so that we can come up with the best solution to optimize our material. And so this is an experimental study that we try to reduce the transmission loss through application of a near-infrared reflective material. As you can see, the top layer was a quantum dots coating, and the sublayer was near-infrared reflective material, which consisted of silver and PET film, and they were all placed on a ceramic substrate. As you can see here, with the absorbance measurements, we can see a significant drop of absorbance at absorption edge wavelength, which really shows that we have a very low absorbance at a higher wavelengths, and also very high transmission. So because we have a very high transmission at let's say longer wavelengths, we can introduce these near-infrared reflective materials so that we can somehow re-emit the shorter wavelengths using the quantum dots layer, while reflecting the higher wavelengths using the near-infrared reflective coatings. And here we measured the surface temperature under the sunlight, and we noticed a very significant reduction between quantum dots with a near-infrared reflective subcoat and quantum dots without a reflective subcoat. Our measurements showed something around 8.1 degree, maximum 8 degrees of surface temperature difference between the two samples. Thank you for your attention, and if you have any questions, I'm more than happy to answer.